I welcome you all for the session 10 on interference of light. Okay. In this session, we shall discuss about the applications of Michelson's interferometer. The first application of Michelson's interferometer is a determination of wavelength of monochromatic light. When the two mirrors are equidistant from A, the field of view is perfectly dark. The mirror M2 is fixed at the position and M1 is moved to get a circular fringes pattern or straight and parallel fringes. The reading the mirror of the micrometer eyepiece is noted R1. The handle H is rotated until 50 fringes appear or disappear at the center. 50 fringes cross the reference crosswire in the case of parallel fringes. The reading of the micrometer eyepiece is noted again R2. If D is equal to R2 minus R1 is the displacement of the mirror position for the crossing of 50 fringes, then D is equal to 50 into lambda by 2. Thus, knowing D, the wavelength of the source is calculated by using the relation lambda is equal to 2D divided by 50. Second application of Michelson's interferometer is to determine the wavelength difference between the monochromatic closely lying spectral lines, and it is also a resolution of spectral lines. In the case of a sodium source, we get two spectral lines D1 and D2 having wavelength lambda 1 and lambda 2 such that the difference in wavelength is very small. When observed in the Michelson's interferometer, each wavelength forms its own fringes which overlap on one another. By adjusting the position of mirror M1, a single fringe pattern having a maximum brightness can be obtained. In this position, the bright fringe due to D1 coincides with the bright fringe due to D2 line. A reading R1 of a micrometer screw is noted. When the handle is turned to move the mirror M1, the fringes go out of step, and further moving the mirror, the fringes with the maximum brightness is again formed. The reading R2 for the position is noted. This is possible only when n plus 1th order of shorter wavelength coincides with the nth order of a longer wavelength. If small d is the distance between the two positions of mirror M1 for maximum brightness, then 2d is equal to n1 lambda 1 is equal to n1 plus 1 into lambda 2, which is equal to n1 is equal to lambda 2 divided by lambda 1 minus lambda 2. Call it as equation number 1. Substituting for n1 in the above equation, we get 2d is equal to lambda 1 into lambda 2 divided by lambda 1 minus lambda 2. Call it as equation number 2. On cross multiplication, lambda 1 minus lambda 2 is equal to, it is the difference in the wavelength which is called as the delta lambda is equal to lambda 1 by lambda 1 into lambda 2 divided by 2t, which is equal to lambda square by 2d, where lambda is the mean wavelength for sodium light. Thus, by knowing the distance d moved by the mirror for positions of a distinct fringe pattern, wavelength difference can be calculated. Okay, here we shall discuss about some of the questions on the session applications of Michelson interferometer. The first question, applications of Michelson's interferometer is option A, determination of wavelength of monochromatic light. Option B, determination of the wavelength of dichromatic light. Option C, determination of frequency of a monochromatic light. Option D, determination of frequency of dichromatic light. We know the Michelson's interferometer applications. The application of one of the application is to determine the wavelength of monochromatic light. Therefore, the answer is option A. Applications of Michelson's interferometer is determination of wavelength of monochromatic light. Answer A is the option. Thanks for the patient listening.